Hello students, in this session we will discuss slope and deflection by Macaulay's method. In previous session we already discussed assumptions of Macaulay's method and we solved one numerical to calculate slope and deflection of simply supported beam which is carrying point load only. Now in today's session we will solve two numericals. In first numerical we will calculate slope and deflection of simply supported beam which is carrying uniformly distributed load and point load both, and in another numerical we will calculate slope and deflection of a simply supported beam which is carrying moment. So let's start today's session. Now let's read data first. So we need to calculate slope at point A and deflection under point B for the beam given in a figure. And we need to take value of EI is equal to 3000 kilonewton into meter square. So in this figure you can see this is a simply supported beam which is carrying UDL of 14 kilonewton per meter, which is for a length of 3 meters starting from point A. The beam also carries point load of 25 kilonewton which is acting at a distance 4 meter from point A. Okay, total length of this beam is 6 meter. Now, before starting calculation, let's discuss steps that we will going to perform for calculation. So, in step number 1, we will calculate reactions RA and RC. Then, in step number 2, we will formulate differential equation, and in step number 3 we will perform double integration of differential equation. In step number 4 we will apply boundary conditions to calculate value of C1 and C2 which are integration constant, and in last step, which is step number 5, we will calculate slope and deflection of a beam at given point. So now let's start with the first step, which is calculation of reaction RA and RC. So for calculation of reaction we need to consider condition of equilibrium. So let's take first condition of equilibrium, which is sigma m is equal to 0, taking moment about A. It means that if I am taking moment about A, then summation of all moment will be 0. And moments are of two types, anti-clockwise and clockwise, and if I am taking anti-clockwise as a negative and clockwise moment as a positive, then I can say that anti-clockwise moment is equal to clockwise moment. Okay. Now in a figure you can see that this reaction RA is passing through point A, so it will not create any moment about point A. Now this reaction RC is acting in an upward direction, and if I am taking moment of this reaction RC about point A, then it will be in a clockwise direction. And moment of this reaction RC will be equal to RC load into distance, which is 6 meter. Now this 14 kilonewton per meter UDL is acting in a downward direction, and if I am taking moment of this UDL about point A, then it will be acting in a clockwise direction, and this moment of this UDL will be 14 into 3, which is total load of this UDL into 3 by 2, which is the distance where this UDL acting from point A. Okay, so now moment of this 25 kilonewton load, again it is acting in a downward direction, and if I am taking moment about point A, then it will be in a clockwise direction. So moment of this point load will be equal to 25 into 4. 4 is the distance, and if I solve this, then answer of RC is equal to 27.16 kilonewton. Now let's apply another condition of equilibrium, sigma V is equal to 0. It means summation of vertical load is equal to 0. So we can say that upward forces are equal to downward forces. So in this given beam, two reactions RA and RC are acting in an upward direction. So I can write down RA plus RC is equal to this two loads, UDL and point load, are acting in a downward direction. So UDL is 14 into 3 plus point load is 25. If I solve this, I will get value of RA is equal to 39.84 kilonewton, which is positive. It means it is acting in a upward direction. So we completed with step number 1. Now let's move to step number 2. So in step number 2, we will formulate differential equation. So here is our differential equation. EI d square y upon dx square is equal to minus mx. So we need to first calculate mx. But before calculating mx, in a simply supported beam, if there is a UDL which is acting on left hand side of the beam, then in that case we need to first generate or create equivalent beam. So in an equivalent beam, I will extend this 40 kilonewton per meter UDL up to end of this beam. It means that between point B and C, I am adding one UDL of 14 kilonewton per meter, which is acting in a downward direction, and I am adding another UDL of 14 kilonewton per meter, which is acting in an upward direction. So ultimately both will nullify their effect and the beam will be same as actual beam, but this kind of the beams are called equivalent beam. Okay, so for calculation of mx, we need to divide this equivalent beam in 3 parts. So let's take AB is the first part, BD is second part, and DC is third part, and we need to take section in each part and we need to calculate moment at each part about section. Okay. So now let's start with section or part AB. So in part AB, I am taking section XX at a distance x meter from point A. And in part AB, I need to take moment about this section XX. Okay. So as per our assumption, we will take origin at A and we will calculate moment on left hand side of the section line. And while calculating moment on left hand side of the section line, all clockwise moment we will take it as a positive and all anti-clockwise moment we will take it as a negative. So in part AB, this reaction RA is acting in an upward direction, and if I am taking moment of this reaction RA about this section line, then it will be clockwise. So I am putting here plus. Okay. Now the moment of this RA will be equal to 39.84, which is load, into distance. So distance between point A and this section is x meter. So 39.84 into x. Now this 14 kilonewton UDL is acting in a downward direction and it will create anti-clockwise moment about this section. So for this UDL, I am putting minus sign over here for anti-clockwise movement, and the moment of this UDL about this section line XX will be equal to 14 into x, which is total load of UDL, into x by 2, which is the distance at which this UDL will be acting from section line XX. So we can say that moment of this UDL about this section line will be 14 into x square by 2. Now let's move to second part, which is BD, and I am again taking section at a distance x meter from point A in portion or part BD. Okay, so let's calculate moment at part BD on left hand side of this section line. So in part BD, this downward UDL of 14 kilonewton per meter is already calculated in part AB. Okay, so let's calculate moment of this upward UDL of 14 kilonewton per meter about this section XX. This UDL is acting in an upward direction, so it will create clockwise movement. So I am putting sign plus over here, and moment of this upward UDL about this section line XX will be 14 into length of UDL. Now length of this UDL is between B to this XX line, okay, which is equal to X minus 3. So moment of this UDL about this XX line will be 14 into X minus 3 into X minus 3 by 2. So we can say that it is 14 into X minus 3 square by 2. Now let's take section in part DC and calculate moment in part DC. So I am taking section at a distance x meter from point A in part 3. Okay, so in part 3 DC, this downward UDL of 14 kilonewton per meter is already calculated and this upward UDL is also calculated. So in part 3, only this 25 kilonewton load will create a moment. This load is acting in a downward direction, so it will create anti-clockwise moment. Okay, so I am putting sign minus over here, and moment of this point load about this section line XX will be 25 into distance between this line of action of this load and section line is X minus 4. Okay. So now let's put value of mx in our differential equation. Then we will get EI d square y upon dx square is equal to minus 39.84x plus 14x square by 2 minus 14x minus 3 square by 2 plus 25x minus 4. Okay. So we are completed with the second step of formatting differential equation. Now let's perform step number 3. So we will integrate this differential equation. So if we integrate this differential equation, then we will get EI integration of d square y upon dx square is dy by dx minus 39.84 integration of x is x square by 2 plus 14 integration of x square will be x cube by 3. 3 multiplied with 2 we will get 6. So 14x cube by 6 plus c1. So I am putting integration constant in first part of the continuous equation as per our assumption. Minus 14 integration of x minus 3 will be x minus 3 cube by 3. 3 multiplied with 2 we will get 6 plus 25 integration of x minus 4 will be x minus 4 square by 2. So here is our first equation for calculation of slope. Now in step number 3 we are applying double integration. So let's integrate the equation again. So if we integrate equation again, then we will get EI into y is equal to minus 39.84 into integration of x square is x cube by 3. 3 multiplied with 2 is 6 plus 14 integration of x cube is x raised to 4 by 4. Multiply 4 with this 6. So we will get 24 plus c1x plus c2 minus 14 integration of x minus 3 cube by 6 will be x minus 3 raised to 4 by 24 plus 25 x minus 4 integration of x minus 4 square will be x minus 4 cube by 3. 3 multiplied with 2 we will get 6. So here is our second equation for calculation of deflection. So we are done with the third step of our calculation. Now in a step number 4 we will apply boundary conditions to calculate value of C1 and C2 which are integration constant. So in a simply supported beam we know that at both the end deflections are 0. So if x is equal to 0, deflection is equal to 0. And if x is equal to 6 meter, which is the full length of this beam, at point C, we also get deflection is equal to 0. So let's apply first condition for calculation of C1, which is x is equal to 0, then y is equal to 0. Put this value in equation number 2, then we will get value of C2 will be 0. Okay, now let's apply second condition, which is x is equal to 6, then y is equal to 0. If I put x is equal to 6 and y is equal to 0 in second equation, then the equation will be 0 is equal to minus 39.84 6 cubed by 6 plus 14 6 raised to 4 by 24 plus C1 into 6 minus 14 6 minus 3 raised to 4 by 24 plus 25 6 minus 4 cubed by 6. If I solve this, then I will get value of C1 is equal to 115.35. Okay, so we completed with step number 4 also, and we get value of C2 is equal to 0 and value of C1 is equal to 115.36. Now let's put value of C1 and C2 in equation 1, which is for slope, and equation 2, which is for deflection. Then these are the final equation 3 that will be used for calculation of slope, and equation 4 that will be used for calculation of deflection. So we are completed with step number 4. Now let's move to step number 5. So in step number 5, first of all, we will calculate slope at point A, and then we will calculate deflection under point B. So in this figure, you can see that at point A, x will be 0, and we need to calculate slope. So we need to put x is equal to 0 in this slope equation, which is equation number 3. Okay, so for calculating slope at point A, we will put x is equal to 0 in equation number 3, which is for calculation of slope. So we will get EI dy A by dx. So I am considering slope at A is equal to x is equal to 0. So the first term will be 0. Again second term will be 0 because x is equal to 0, plus 115.36 minus x minus 3 means 0 minus 3. As per our assumption, if x minus a is less than 0 means negative, then we will neglect it. So we will neglect this term 14x minus 3 cubed by 6, and again this term 25x minus 4 will be minus 0 minus 4 is minus 4. So we will neglect both this term. Okay, so we get value of theta A. Theta A is a slope at point A is equal to 115.36. I am taking this EI in numerator, then it will be equal to 115.36, and in a given data value of EI is 3000. So I get answer of theta A is equal to 0.038 radian. So here we calculated slope. Now let's calculate deflection under point B. So for calculating deflection at point B is at a distance 3 meters from point A, which is our origin. So we need to put x is equal to 3 in equation number 4, which is deflection equation. Then we will get deflection at point B. So if I put x is equal to 3 in equation number 4, then I will get EI into YB is equal to minus 39.84 3 cubed by 6 plus 14 3 raised to 4 by 24 plus 115.36 into 3 minus 14, 3 minus 3 raised to 4 by 24 plus 25, 3 minus 4 raised to 3 by 6. If I calculate this, then I will get YB is equal to 214.05 upon EI. So value of EI is 3000. So I will get value of YB is equal to 0.071 meter, which is in a positive. So I can say that deflection will be in a downward direction. Okay. So we completed with the sum. Now let's solve another sum, which is calculation of slope and deflection for a simply supported beam carrying moment. So in this sum, we will calculate slope and deflection at point C using Macaulay's method. So in given figure, you can see this. The beam is simply supported beam which is carrying moment at point C, and total length of this beam is 3 meter. So let's start with calculating reactions RA and RB. So for calculating reactions RA and RB, we need to consider condition of equilibrium. So let's take first condition of equilibrium, which is sigma m is equal to 0, taking moment about A. So we can say that anti-clockwise moment is equal to clockwise moment. So in our case, reaction RB, which is acting in upward direction, will make anti-clockwise moment about point A, which is equal to RB into 3. And this 4 kilonewton into meter, this moment is also anti-clockwise moment. So we are adding this moment here, plus 4 is equal to 0. So we get value of RB is equal to minus 1.33. So for calculation purpose, before calculation, we assume that both the reactions are acting in a upward direction. But in case if we get value of any reaction negative, then it means that that reaction is acting in a downward direction. So in our case, we are getting value of RB is equal to minus 1.33. It means that reaction RB is acting in a downward direction. Okay, so now let's apply second equation for calculating reaction RA. Second condition of equilibrium, sigma V is equal to 0, means summation of vertical force is equal to 0. It means RA plus RB is equal to 0. Here RA is acting in a upward direction, which is positive, and RB is acting in a downward direction, which is negative. So we can say that RA is equal to plus 1.33 kilonewton. So this is the calculation of step number 1. Now let's move to step number 2. So in second step, we will calculate mx and then we will formulate differential equation. Okay, so here is our differential equation. EI d square y upon dx square is equal to minus mx. Now first of all, we need to calculate mx, and for calculating mx, first of all we need to divide this beam in two different parts. So let's take AC as the first part and CB as the second part, and if I take section in both the part, and then I need to calculate moment in both the part. So let's start with first part, that is AC. Okay, so here I am taking section XX at a distance x meter from point A. Okay, now I need to calculate moment at part AC about this section line XX. So here in part AC, this reaction RA, which is acting in an upward direction, will create clockwise moment about this section line XX, which is equal to 1.33 into x. Now in second part, if I take section XX at a distance x meter from point A, then the moment of this 4 kilonewton into meter moment about this XX line will be minus 4 x minus 0.6 raised to 0. Okay, so here we need to recall our assumption, and the assumption was whenever distance is multiplied with moment, quantity distance x minus a will be written as x minus a raised to 0. Okay, so in our case moment is 4 kilonewton into meter, which is anti-clockwise, so I am putting minus sign over here, and distance between this moment and x-axis section is x minus 0.6, so I am writing x minus 0.6 as x minus 0.6 raised to 0. So this is our mx calculation. Now if I put value of mx in this differential equation, then I will get ei d square y upon dx square is equal to minus 1.33x plus 4x minus 0.6 raised to 0. Now in step number 3 we will integrate this differential equation. Okay, so by integrating this differential equation, we will get ei dy upon dx is equal to minus 1.33x square by 2 plus c1 plus 4x minus 0.6 raised to 1 by 1. So this is our first equation for calculating slope. Okay, and if we integrate this equation again, then we will get equation ei into y is equal to minus 1.33x cubed by 6 plus c1x plus c2 plus x 4x minus 0.46 raised to 2 by 2. So this is our second equation which we will use for calculation of deflection. Okay, now in step number 4, we will apply boundary conditions to calculate value of C1 and C2. And for simply supported beam, we know that at both extreme end, means at x is equal to 0 and x is equal to L. In our case, L is equal to 3. At both the end, we get deflection is equal to 0. So let's apply first boundary condition, which is x is equal to 0, then y is equal to 0. Put this value in equation number 2, then we will get value of C2 is equal to 0. Now let's apply second equation, second boundary condition, which is x is equal to 3, then y is equal to 0 in equation number 2. Then we get equation as 0 is equal to minus 1.33 3 raised to cube by 6 plus c1 plus 4 3 minus 0.6 square by 2, and ultimately I will get value of c1 is equal to minus 1.845. So if I put value of C1 and C2 in equation number 1 and in equation number 2, then I will get final equation number 3 for calculation of slope and equation number 4 for calculation of deflection. Okay, so now let's move to step number 5, where we calculate slope and deflection at point C. So for calculating slope at point C, we need to put x is equal to 0.6 in slope equation. So we get value of theta is equal to minus 2.0844 upon EI. In similar manner, if I put x is equal to 0.6 in deflection equation, then I will get yc is equal to minus 1.155 upon EI. Okay, so this is the end of this session. Thank you.